Let us consider an arithmetic sequence. Now, in order to define an arithmetic sequence, we need a first term and we need the common difference. So let us suppose that A represents the first term of the sequence and D represents, and D is the common difference. Now, how to define the common difference? All you have to do is take any term and subtract the previous term from it to get the common difference. That means the arithmetic sequence is going to be given by the first term A followed by the second term. In order to find out the second term, we take the first term and add the common difference to it. So A plus D is going to give us the second term. Then we're going to again add one more common difference to the second term. So we have A plus D added to D. So that gives us A plus 2D, and this is going to give us the third term. Similarly, we can find out the fourth term. So that's going to be A plus 3D. And if we generalized it, then the nth term of the sequence is going to be given by A plus n minus 1 times the common difference D. So we've already discussed what arithmetic sequence were. The example will be if we consider A to be equals to 2 and the common difference as 3, then 2. So add the common difference 3 to it, that gives us 5. Add the common difference 3 to 5, so that gives us 8. Then we have 11. So this is going to be an arithmetic sequence. This is an infinite arithmetic sequence. Okay. Similarly, let's also discuss geometric sequence. Similarly, let's also quickly recap what geometric sequences are. So here we are also going to define two parameters. So let's say A is the first term. We're using the same symbol for the first term. So let A be the first term, and we're going to consider R to be the common ratio, because in the case of a geometric sequence, we need ratios. Now, to define the geometric sequence, we consider the first term, that's A. This will get multiplied with, the first term will get multiplied with the common ratio to give us A times R, and this is the second term. To find out the third term, we take the second term AR and multiply with R to get AR squared, which will give us the third term. We can continue this, and the nth term of the sequence is going to be AR raised to the power of n minus 1. So this is how we can define a geometric sequence. For instance, let us consider A to be equals to 2 and R to be equals to 2. Then in that case, we have 2. Next will be 2 times 2, that's 4. Then 4 times 2, that's 8. 8 times 2, that's 16. And this is going to continue. This is an infinite geometric sequence. Now, let's do one thing. Let's take the first term of each of the two sequences and multiply them with each other. So we have 2 times 2. That's going to give us 4. Next, we have the second term of the arithmetic sequence, that's 5. Let's multiply it to the second term of the geometric sequence, which is 4. So 5 times 4, that's going to be 20. Next, we have 8 multiplied to 8, so that's 64. Then we have 11 multiplied to 16, so that's going to be 176. Now this, what we have is a very new type of sequence, and this is referred to as the Arithmetico-Geometric sequence. So, Arithmetico-Geometric sequence, this has been derived by taking the first term of an arithmetic sequence and a geometric sequence and multiplying them with each other. Then the second term will be take the second term of each of the two sequences, multiply them together. So we do this to each of the terms, and the new sequence that we get is going to be referred to as the Arithmetico-Geometric sequence. Let us generalize this idea. Now let's do one thing. Let's define a very new type of sequence where the first term is A. Then what we do? We define the next term as we take A plus D and multiply it with a common ratio that's going to be defined by R. Then we take A plus 2D and multiply it with R squared. Then we have A plus 3D multiplied with R cubed. What is this giving? Let's go to the nth term as well. We have A plus n minus 1 times D and multiply it with R raised to the power of n minus 1. All we have done is multiplied the corresponding terms of the arithmetic as well as the geometric sequence. Now, this is neither an arithmetic sequence nor a geometric sequence, but it gives the feel that it's a combination of both of them. So this general type of sequence will be referred to as the Arithmetico-Geometric sequence. So let's try to understand this with the help of an example. Now let us suppose we have a sequence whose first term is 1, the second term is 3x, the third term is 5x squared, and the fourth term is 7x cubed, and our goal will be to find out its nth term. Now, this given sequence is neither an arithmetic sequence nor a geometric sequence, because for it to be an arithmetic sequence, it needs to have a common difference. Now here, if we do the second term minus the first term, that's not equals to the third term minus the third term minus the second term. Because this is not following, so we cannot say that it's an arithmetic progression. Also here we cannot say that it's a geometric sequence as well, because if we take the second term, that is 3x divided by 1, that gives us 3x, and this is not the same as taking the third term and dividing by the second term. So we are not getting the same common ratio. So this is this is also not a geometric sequence. However, if we look closely at the given sequence, then we can say it's composed of two sequences. Let's say if we consider the sequence 1, the coefficient of x, where the first term is 1, then we consider the next term to be 3, followed by 5, then 7. This is a arithmetic sequence, or we're calling it arithmetic progression. And we have the first term is 1, the next term is x, then we have x squared, then we have x cubed. Let this be a geometric progression or a geometric sequence. Then what is the nth term of the arithmetic progression? Then in that case, the nth term is going to be given by the formula a plus n minus 1 times the common difference d. So here the first term, that's 1, added to n minus 1 times the common difference d, so d is going to be 2. So when we simplify this, we're going to get 2n minus 1. So this is the nth term of the arithmetic progression. And if we consider the geometric progression, so here the nth term, that's given by a multiplied to r raised to the power of n minus 1. So that will be equals to, so we have the first term, that's 1, multiplied to the common ratio r raised to the power of n minus, this is x, the common ratio, that's x raised to the power of n minus 1, which means that we have x times x raised to the power of n minus 1. Now, to define the nth term of the original sequence, the Arithmetico-Geometric sequence, all we have to do is take the nth term of the arithmetic progression, so that's 2n minus 1, and multiply it with the nth term of the geometric sequence, and that's x raised to the power of n minus 1. So this is going to be the nth term of the given sequence. Let's do one more problem. So here we need to determine the nth term of the sequence 2, negative 5x, 8x squared, negative 11x cubed, and so on. Okay, now this is neither an arithmetic sequence nor a geometric sequence. However, what we'll do, we'll try to break it down such that one of the sequences is going to be an arithmetic and the other sequence is going to be geometric. Let's try to break it down. So let us suppose that 2, negative 5, 8, these are the coefficients of x. 2, negative 5, positive 8, negative 11. Let's say this particular sequence is an AP, but we need to verify that it is actually an AP. So for this, we need to have a common difference. So if we do negative 5 minus 2, so that gives us negative 7. But this is not equals to the third term minus the second term, which means that this is not an arithmetic sequence or an arithmetic progression. So that means we have to consider some other alternative. So suppose, let's say we drop the negative sign. So we only consider the positive values. So we have 2, 5, 8, 11. Now, is this an arithmetic progression? Yes, this is an arithmetic progression, because if we take the common difference between the second term and the first term, that means 5 minus 2, that will be equals to 3. This is also equals to 8 minus 5, which is also equals to 11 minus 8. So that means we have obtained a arithmetic progression. Now that we have the arithmetic progression where the first term is 2 and the common difference is 3, we can define its nth term. Then the nth term of the arithmetic sequence is going to be the first term added to n minus 1 times the common difference 3. So this is going to give us 3n minus 1. So that's going to be the nth term of the given arithmetic sequence. Then we'll consider now the coefficient of each of the constants, which is the variable x here. Here we will consider the first one to be positive 1, the first term to be positive 1, followed by coefficient of 5. We'll consider the coefficient of 5 to be negative x, the variable coefficients. Then coming to the third term, we have 8x squared. If the coefficient of the constant 8, that's going to be x squared. Then we have negative x cubed and so on. Now this is a geometric sequence, or it's a geometric progression where the first term a, that's going to be 1, and the common ratio r, that's going to be negative 8. Now we have to check if it is true that it's a geometric progression or not, because if we take the second term, that's negative 1, divided by the first term, so that's going to give us negative x. And this is the same as taking the third term x squared and dividing it by the second term negative x. So that also gives us the common ratio of negative x. We can check that out with negative x cubed divided by x squared. That means take the fourth term divided by the previous term, which is the third term, and that should give us the common ratio as negative x. So this is indeed a geometric progression. So now that we have the first term and a common ratio, then the nth term of the sequence is going to be given by a times r raised to the power of n minus 1. So we have 1 multiplied to negative x raised to the power of n minus 1. However, what we'll do, we'll pull out this negative sign to get negative 1 raised to the power of n minus 1 multiplied to x raised to the power of n minus 1. So we have the nth term of the arithmetic progression, we have the nth term of the geometric progression. So that means the nth term of the Arithmetico-Geometric sequence an, that's going to be given by 3n minus 1 multiplied to x raised to the power of n minus 1 times negative 1 raised to the power of n minus 1. So this is going to be the required nth term. So we have now established the fact that if we consider the first term to be a, followed by the second term, which is a plus d multiplied to r, then and the third term, that's a plus 2d multiplied to r squared, followed by a plus 3d multiplied to r cubed. This keeps on continuing till we get to the till we reach the nth term, which is given by a plus n minus 1 times d whole multiplied to r raised to the power of n minus 1. Let's consider a finite sequence for this. What we have obtained here is an arithmetico-geometric sequence. And if we take the sum of each of the terms, so that means we have a added to a plus d times r added to a plus 2d times r squared added to a plus 3d times r cubed. This keeps on going to give us a plus n minus 1 times d multiplied to r raised to the power of n minus 1. Then what we get is an arithmetico. This is going to be an arithmetico-geometric series. So that's the difference between a sequence and a series. So summing up each of the terms in the sequence gives us a series. For instance, let us consider the following series. We have 1 added to 2 over 3, added to 3 over 3 squared, added to 4 over 3 cubed, and so on. We need to find out the nth term of the sequence. Okay, let us begin. So first what we'll do, we'll have to separate the arithmetic progression from the geometric progression. Let's find out the arithmetic progression. So here, if we're going to rewrite the series first. So let's say we rewrite the first term as the product between 1 with itself, 1, added to. Next, we have 2 over 3 as the second term, but we're going to rewrite it as 2 multiplied to 1 over 3. Added to, we're going to take the third term, 3 over 3 squared, and rewrite it as 3 multiplied to 1 over 3 squared. And the remaining terms. So here, what we can do, we can say that we have two sequences. One of the arithmetic progression that's defined by taking the terms as 1, 2, 3, 4, such that the nth term is simply going to be n. And we have a geometric progression whose first term is 1, followed by the second term, that's 1 over 3. Then we have 1 over 3 squared, and this continues such that it gives us 1 over 3 raised to the power of n minus 1 as the nth term. Now, what we can do, we can define the nth term of the arithmetico-geometric sequence. So, nth term, thus an, that's going to be equals to, take the nth term of the arithmetic progression and multiply it with the nth term of the geometric progression, which means we now have n over 3 raised to the power of n minus 1, which is going to be the nth term of the given arithmetico-geometric series. Okay. So we started out by defining a sequence, the arithmetico-geometric sequence, where we also found out the nth term by breaking the given sequence into its corresponding arithmetic sequence and the geometric sequence. Using the same idea, we found out the nth term of the series. Now comes the next important question. What is the sum of the n terms of any given arithmetico-geometric series? Okay, so let's go to our next concept, which will be the sum to n terms of an arithmetico-geometric sequence.